Chandrashekar Radhakrishnan. He is now working as a principal project scientist at the Center for Quantum Information based on IIT Madras. And before that, he worked as associate professor of the École Numérique in Paris, and also he was a postdoctoral fellow at New York University. His area of interest is the quantum information theory, the resource theory, and relativistic quantum information, and also the quantum internet. And he also loves these mathematics, group theory, and the Laplace transform and these things. And also he has strong interest on this statistical physics as well. So today he will be talking about this multipartite quantum coherence and quantum coherence and a perspective. I think it is written twice, right?
It was an error.
So please start.
Thank you, Professor Alok, and thank you for the introduction.
Your voice is breaking still.
It's breaking still. Okay. Thank you, Professor Alok, and thank you for the introduction. And I'd also like to thank the organizers for inviting me for this, to give this lecture. So I'm extremely sorry about this mistake in the title. It should have been multipartite quantum coherence and quantum discord perspective. So what I will do in this talk is give a brief introduction about quantum coherence. Then I will move over to explain the two different forms of quantum coherence, which can arise due to superposition between the levels and due to interaction between the qubits. Then I will show the usefulness of quantum coherence in spin models, and then I will take give a brief or a broader view about relativistic effects on quantum coherence. By relativistic effects, what I mean is when we have a multipartite system in which some of the parties are moving with an acceleration, what is the effect of this acceleration on quantum coherence? And finally, I will quickly give an overview of one of our recent works on multipartite quantum discord. Okay, so is there a question already, or like, sorry. Okay, so to give a brief introduction to quantum coherence, we all know about entanglement. And yeah,
Radhakrishnan, your voice is really breaking. I mean, it is my problem, or organizers, are you here?
Can you hear me clearly? Oh, okay, then, thank you. Okay, so shall I continue? Okay, so we all know that entanglement is a resource for quantum information processing tasks, in that it has been used in several protocols like quantum teleportation, quantum secret sharing, superdense coding, and so on. So another important property in quantum physics is coherence. And by the word coherence, what we understand is a general idea. What we had was we look at the off-diagonal elements of the system, but this is an intuitive idea. And there was no proper method to quantify coherence in the system. Okay, just a moment, like there are too many messages. Okay, I'm sorry.
Just excuse me, it was not relevant. It just was addition. No, not to your talk. Sorry.
Okay, I'm sorry. Like I didn't realize that. So a formal method for quantifying coherence was lacking, and this gap was filled up through this work. by Baumgart's, Kramer, and Plinio. In their work, they introduced a method for quantifying coherence based on 3 important points. One of them was how to identify the incoherent state by yeah, just give me a moment, like, let me check. Can I borrow your paper? Yep. Oh, okay. Hello. Am I audible now? Hello. Am I audible now? Okay, I'm sorry. I tried using a different set of speakers and I couldn't hear anything with them as well. Okay, I will continue this from here. So to quantify coherence, there were 3 important things, 3 important quantities were introduced. One was the incoherent states, that is the states with 0 coherence. Then maximally coherent states, that is states with the maximum amount of coherence in them. And finally, incoherent operations, states which do not create any coherence in their operation when you use them over the states. Okay. Now, using these, coherence measures were constructed. There were some important properties a given coherence measure should have. The primary among them is it should be 0 only for incoherent states. Then it should obey monotonicity. By monotonicity, what we mean is when you have a measure of coherence, it should vanish for incoherent states and it cannot increase under incoherent operations. Okay. And the third property is convexity. That is, when you take 2 quantum states and mix them, coherence cannot increase under a mixture of quantum states, under mixing of quantum states. This is convexity. So based on these properties, the authors for Baumgart's, Kramer, and Plinio, they introduced a set of coherence measures, and for this they used a distance-based measure. By distance-based measure, what it means is if I have a quantum state or a density matrix rho, I find the distance to the closest state which lacks the particular property which I am measuring in rho. For example, if I am measuring quantum coherence in rho, then I find the distance to the closest incoherent state. So this is what a distance-based measure does. Mathematically, a distance-based measure should have the following properties. They are: the distance-based measure should always be greater than 0 when it is measured between 2 density matrices, 2 points x and y. Let's say this is a classical thing and we are looking at 2 points x and y. So we are finding the distance between the points x and y. If x is not equal to y, then the distance is greater than 0. And for x, for the distance from x to x should be equal to 0. Then the third point is the distance d from x to y should be equal to the distance d from y to x. That is, you measure one way, it should be equal to the value you measure the other way around. Apart from these three properties, there is another property called the triangle inequality, where you consider 3 points x, y, and z, and you measure the distance between pairs of points. If you measure the distance between the pairs of points, and if the distances satisfies this inequality, then the distance measure is said to satisfy triangle inequality. Okay. So if a measure satisfies the distance properties as well as the triangle inequality, we call that measure as a metric. Now, coming back to the earlier question, I said that we take a quantum state and measure the distance to the reference state. Now, the question is the reference state I'm using unique in the situations we are working at? When you look at the quantum states, there is nothing like a unique reference state. There are several states with zero amount of the property. For example, for a given density matrix rho, I can have 3 different density matrices which are incoherent. So in that case, how do we measure the coherence? Instead of measuring the distance to any one of them, we can actually choose the distance to the closest reference state. That is the principle behind the minimization we use in measuring quantum properties. Okay, for example, when we have an entanglement measure, we can find the distance to the closest. We find the distance from the density matrix rho to the density matrix sigma. And the expression is given here, and we can immediately see that the measure is not symmetric in rho and sigma. So if it is not symmetric in rho and sigma, what happens is it will not obey this property 3 of the distance measure we have here. Okay. So the relative entropy of coherence, although it's a measure of coherence, it is strictly not a distance. It's just a divergence. So the other measure we have is the L1 norm of coherence. In L1 norm of coherence, we find the distance from the density matrix rho to the closest incoherent state. This means that we are essentially summing up the off-diagonal elements of the density matrix. Okay. So these are the 2 measures which were initially introduced. Later on, I mean, much before quantum coherence, another distance measure was introduced based on entropy functional, and this was called as the Jensen-Shannon divergence measure. This measure is simply an extension of the relative entropy measure. As we can see here, the relative entropy measure is not symmetric in rho and sigma. And also there is a second problem it might give rise to when the support, that is the number of eigenvalues of sigma, is less than that of rho, the measure will blow up. Okay. So this is essentially not a desirable feature. So what we can do is instead take the relative entropy from rho to the midpoint, that is rho plus sigma by 2, and then from sigma to rho plus sigma by 2, and take a sum of these 2 things. Okay. So this new measure is called the Jensen-Shannon measure of divergence. And this was introduced in a classical sense for probabilities by J.J. Lin, but a quantum extension of that was later done by Lamberti and co. So in the Jensen-Shannon divergence measure, if we check out for the properties, it verifies the properties of a distance. but it does not verify the triangle inequality. So the Jensen-Shannon divergence is not a metric. If we want a metric, we can use the square root of the Jensen-Shannon divergence, which obeys the properties of a distance as well as the triangle inequality. So in our work, we introduced a coherence measure based on the Jensen-Shannon divergence. So the coherence measure, the distance measure based on Jensen-Shannon divergence, we can write it in terms of for a density matrix rho and the reference state sigma, we can write it simply in terms of the entropies of the system. And this expression, we can see that is the entropy of the joint system, that's rho plus sigma, where we subtract the entropies of the individual systems. Okay. When we consider sigma to be the separable state, then this distance measure can measure the amount of entanglement in the system. And this measure was introduced by Plastino in 2008. And this is essentially a mirror of the relative entropy of entanglement measure introduced in 1999 by Plinio and Vedral. Similarly, when we consider the incoherent state to be the reference state, we can introduce a quantum coherence measure. And we introduced this in our work. And then we looked at the quantum coherence from the point of view of superposition. Okay, so when we look at a multipartite system, like here in this picture over here, the black dots represent the qubits and the arrows represents the correlations between the qubits, the red colored arrows. I can imagine that each dot has some kind of correlation between them. And also there is a superposition between the ground state and the first excited state of the qubit. Okay, so we can see that there are two different forms of superposition coming out, one due to the levels of the qubit and the other due to the correlation between the qubit. These two forms give rise to two different forms of coherence. The coherence due to the interaction between the qubits is what we call as the intrinsic coherence. And the coherence due to the superposition between the levels, we call it as the local coherence. And the total coherence is usually a composition of both the intrinsic and the local coherence. And just say using the word composition because it is not necessarily an additive, like they don't combine additively to give the total coherence. Okay, so how do we measure these two forms of coherence? So measuring the two forms of coherence is very simple. For the intrinsic coherence, we can measure the distance from the density matrix rho to either the separable state or the product state. Okay. So in a separable state or a product state, what we have is there is no correlation between the individual members of the qubit. So we'll essentially have only if we measure from rho to sigma s, we'll essentially have the intrinsic coherence, which we can also call as global coherence because it is present more between the qubits. Okay. Then to measure the local coherence, what we do is we consider this product state and measure the distance to the diagonal form of the product state. And this we call as the local coherence. So if we look at the picture of the state space, if I have a density matrix rho here, I can find the distance to the closest product state, and that distance is my intrinsic coherence. from the product state to the diagonal of the product state, I have the local coherence. In fact, I can directly find the distance from the density matrix to the diagonal of the density matrix. That's the product of the diagonal of the product, which I call as the total coherence. And we can see that since we are using this Jensen-Shannon metric, these three lines form a neat triangle, and the total coherence here is less than or equal to the sum of the local coherence and the intrinsic coherence. So we can see that this two forms of coherence, actually, as I mentioned earlier, they do not combine in an additive manner. Okay. So when you're looking at the local and intrinsic coherence, we wanted to look at some particular example for that. So one of the example we had in mind was a spin model, where we could actually measure the total coherence as well as the local and intrinsic coherence. And for that, we consider a transverse Ising model with a Hamiltonian as given here, and we've estimated the coherence, total coherence, local coherence, and the intrinsic coherence in this system. And we can see that the total coherence, when j by lambda is 0, the total coherence is at some particular value. Let's say this is around 0.5 or 0.55, and it moves on, increases, and saturates to some value above something like 0.7. Okay, so at this point, when j by lambda is equal to 0, the ground state of the Hamiltonian is the Bell state, which is 0, 0, minus 1, 1. And for the Bell state, we do not have any local coherence because there is no superposition between the levels in both the qubits. This is a 2-qubit system, and both the qubits, they do not have any internal superposition. So what happens is there is no local coherence. So the local coherence is 0 here, and all the coherence is global coherence, and then it keeps decreasing as we move from 0 on to 2. We find that the intrinsic coherence decreases, whereas the local coherence keeps increasing. When we go to large values of j by lambda, let's say at j by lambda equal to 2, the state is completely separable state. This is the minus state. This is the x basis minus state. And this state is a product state, and also the only coherence in the state is the coherence due to the superposition between the levels 0 and 1, which we can see here. These two states have the superposition 0 and 1. So the local coherence is maximum at j by lambda equal to 2, and the global coherence or intrinsic coherence is minimum at this point. Now we can see that the global and the local coherence are complementary to each other, and as we increase the strength of the interaction, it switches from one form to the other. Okay, so this was a simple 2-qubit model. So the next model we looked at is the Heisenberg XXZ spin chain, where we considered 11 spin system and did an exact diagonalization procedure to find the density matrix and the quantum coherence in the system. We considered XXZ model, where the interaction strength of the X and the Y, these two things are the same, and the Z is different. So the Jx equal to Jy and Jz is different. So we can write this as delta times sigma z. And this model in general, it's known that this model has 2 points where there is a phase transition. At the point delta equal to -1, there is a phase transition from the ferromagnetic phase to the this axial ferromagnetic phase to the planar antiferromagnetic phase. Okay, and at delta equal to 1, there is another phase transition from the planar antiferromagnetic to the axial antiferromagnetic phase. Okay, so there are two phase transitions, and we measured the quantum coherence to see what happens in these in this system. We can see that initially when delta is at -2, that's in the ferromagnetic phase, the quantum coherence is 0. This because all the spins are in one state, and the density matrix has only one component, and it's an incoherent state. Okay, and exactly at delta equal to -1, you can see that there is a sudden change, and the coherence starts increasing, and then it starts decreasing again, and then there is a slow change in the quantum coherence after delta equal to +1. So we can see that the coherence actually changes and saturates at some finite value. And this finite value where it saturates is for delta equal to very much greater than 1. The ground state is similar to GHZ or a Neal state, where we have superposition of only 2 terms. Okay. So now we looked at the coherence of the whole system. Now we can look at the coherence of bipartite pairs in the system. If we look at the coherence in the bipartite pairs, we can see that the coherence between 2 neighboring qubits like 1 and 2 is actually much higher when compared to the coherence between the distant neighbors like 1 and 6. So the two-side coherence, see, 1:n, where n is when n increases, when n is far from 1, decreases with the distance. Okay. So the next model we looked at was a Heisenberg XY model. So in the previous model, we did a computational method to calculate the quantum coherence, and we had something like 12 spins in the system. Okay. Now we looked at an infinite spin chain, and we considered a XY model, and this is the Hamiltonian of the XY model, where the anisotropy parameter gamma can take values from -1 to +1. And here we considered a spin model which also had a Zyloshinsky-Moria type interaction. So this is not just a spin-spin interaction. There was also some spin lattice interaction coming in. So for this model, the two-side density matrix, that is for the density matrix for the ith qubit and the I plus r qubit is X state, where the elements of this density matrix is given by the it's given by the expectation values of the spin operators. Okay. So again, we used the quantum coherence measure based on the Jensen-Shannon divergence. So for the model Hamiltonian we considered here, initially we considered a gamma value of 0.5, and when we consider gamma value of 0.5, we have a XY model, and for the XY model we consider different values for the D. D is the Zyloshinsky-Moria, that's the spin lattice interaction strength. When you consider D is equal to 0, then it's just a XY model without DM interaction. And we found that the quantum coherence actually exhibits a non-analytic behavior at J equal to 1, indicative of a quantum phase transition. To see this, actually we plotted the first derivative of the quantum coherence as a function of the interaction strength. Okay. And here we can see that when D increases, like when D is equal to 0, the non-analytic behavior is more pronounced than when D equal to 1. So the red dots are for the D equal to 0 and the blue dots for the D equal to 1. Okay. So then we considered gamma equal to 0, where we looked at the XX model, and in the XX model we again find that the model displays or locates the phase transition at j equal to 1, and we also look at gamma equal to 1, which is the transversizing model. From all these things, we can conclude that quantum coherence is actually a good indicator of quantum phase transition. Now, the question is, like, we have been traditionally using entanglement as an indicator of phase transition. So why do we need another measure like quantum coherence to find phase transition? So entanglement as such, entanglement can find phase transition, but the problem we have is we can use a 2-point, I mean, like the reduced density matrix with the bipartite reduced density matrix to find the phase transitions. But if we want to look at systems with more than a bipartite reduced density matrix, like when we want to do computational methods to calculate the entanglement, we will not be able to calculate entanglement successfully because there are no known good measures, I mean, like very specific measures for measuring multipartite entanglement. And multipartite entanglement measures which exist are also not so easy to calculate. But if we look at quantum coherence, it is actually very easy to calculate the quantum coherence of a system, and we can do it for multipartite systems very easily. So multipartite coherence has the extra edge in giving extra edge that it can be used to measure quantum coherence of much larger subsystems or systems. Okay. So so far we were looking at quantum coherence of systems which were not moving, or which were in an inertial frame of reference. Next work I'm going to describe is a recent article in which we described quantum coherence in non-inertial frames. So usually we work in Minkowski space, where we have a 3 space and 1 time dimension. When we have a non-inertial frame, we consider Rindler coordinates. In our discussions, we are considering 1 space and 1 time dimension, and the space-time diagram of our system is given here. So you can see the past light cone, which is given here with the symbol P, for which mod z equal to minus t, and the future light cone for which mod z equal to plus t. And then this light cones actually split the system into 2 regions, the left and the right regions, which we mark as 1 and 2. And the coordinates for the system are the time. So xi is the space-like coordinate, and tau is the proper time, and a is the acceleration of the system. So here we consider a tripartite system with Alice, Bob, and Charlie, and each one of them have a monochromatic detector with different frequencies. So let's say Alice has frequency 1, Bob has omega 2, and Charlie has omega 3. And let us consider a GHZ type state. So the ground state for the in this system is 0 of omega I, and the subscript m here stands to represent that we are looking at the Minkowski coordinates. Okay, Minkowski space-time. Okay, so the excited state in the Minkowski space-time can be obtained from this ground state by using a Minkowski creation operator. That's A omega I data. Okay. So now let us assume that Charlie is moving with a uniform acceleration. The wave function is highly delocalized in space because Charlie is moving with an acceleration. So we can specify the frequency state with frequency omega 3 using either the Rindler or the Unruh coordinates. Okay. So the field in this coordinate, the field initially in the Minkowski space can be expanded in this form, where A and A dagger are the annihilation and creation operators in the Minkowski space. In the Unruh space, we use capital A and capital A dagger for the annihilation and the creation operators. Similarly, for the Rindler coordinates, we use small b. Now, these three operators, these three sets of operators satisfies the following commutation relation, where the following commutation relations and the creation operators in the Minkowski and Unruh basis do not mix with each other because the Minkowski mode is a product of several Unruh modes. So the Unruh vacuum state can be written in terms of the Rindler state as 0 is equal to tan hyperbolic cosine hyperbolic times. It can be written in terms of the modes in the Rindler 1 region and Rindler 2 region. Okay, and the Unruh ground state does not coincide with the Rindler ground state. So here we consider the wave function is sharply peaked in, or narrowly peaked, not sharply peaked, is narrowly peaked. And so the creation annihilation operators will obey these following commutation relations, where we can see that instead of delta omega 1 omega 2, that is we'll have a 1 here, and then we have the creation operator of the Minkowski space can be split into the creation operator of the Unruh space as the left and the right parts. And here we have contributions coming from the left and the right parts, where QR square and mod QR square plus mod QL square equal to 1. So based on these, we can make a map from the Minkowski to the Unruh to the Rindler mode, and we can write down the Rindler state as follows. Here we can see that there are two contributions coming from the left and the right regions. And here we apply a very important approximation called the single mode approximation. In the single mode approximation, what we do is we consider that QR equal to 1 and QL equal to 0. That's we consider that all the information is in one of the regions. Under these conditions, we can directly connect the Minkowski and the Rindler modes. We can directly connect this Minkowski creation and the Rindler creation operators through a set of transforms, where the transform S is equal to exponential of these Rindler operators, and we can see that this is familiar, very familiar, and quite close, looks very similar to the two-mode squeezing operator. Okay. So the GHZ state can be, the GHZ, in the GHZ state, we can actually substitute the ground state and the excited state and derive the relativistic state with the relativistic dynamics. Okay. So here the cosine hyperbolic R and omega are all defined here, and we actually make this transformation this is what the ground state and the first excited state in the Rindler mode looks like. And to measure the coherence in our work, actually we used the L1 norm of coherence. The L1 norm of coherence, we just have to add the off-diagonal elements in the system. Then we had the global coherence, and this is the definition for the global coherence and local coherence in the L1 norm of coherence. Okay. So when we look at a general picture of what is happening, we have three parties: Alice, Bob, and Charlie. Alice and Bob are either at rest or in inertial motion, and Charlie is in non-inertial motion. So what happens is Charlie's information is split up into two parts, Rindler 1 and Rindler 2. So if you want to continue the calculations, we have to trace out one of these two parts, either Rindler 1 or Rindler 2, and compute the coherence or entanglement in the remaining part. So the GHZ state with both the Rindler 1 and Rindler 2 region is given here, and we trace out the second Rindler mode in our work, and we find the quantum coherence of the system. We get an exact analytic expression for the quantum coherence in terms of the polylog functions. Okay, then we look at how the coherence varies. Here, I'd like to say that we considered a very general form of GHZ state, where instead of 1 by root 2 as a normalization factor, we used cos theta and sin theta. Okay, so when theta equal to pi by 4, we have the maximally entangled GHZ state, and we can find that the coherence, which is 1 initially, decreases with the acceleration, but beyond a point, it does not decrease, and it just saturates at a finite value. So the same result holds for any value of theta. And then we look at the quantum coherence of W state. And again, we consider a parameterized W state where we parameterize the superposition terms using sin thetas and phis using the spherical polar coordinates. For this state, we find the analytic expression for the quantum coherence. And again, like since there are two parameters, we have a contour plot for this system. And we can see that for the region, this is a place where the W state is as the coefficient, I mean, like the normalization factor of 1 by root 3, these two places. And at these places, the coherence is maximum. And the rest of the places, it is not so high, but in all these things, they actually saturate and they get to some minimal value. Okay. So the next thing we looked at was this was only a finite, I mean, like three-party system. So what happens if there is a multi-party system? By multi-party system, I mean like arbitrary number of qubits in which let's say I have a capital N number of qubits in which small n number of qubits are moving. So I'm considering a system like the one shown here, where the circles are the qubits. And let's say the blue circles are at rest and the red circles are in inertial motion. If I consider a n qubit GHZ state with capital N number of qubits, out of which small n are moving with an acceleration, then the quantum coherence in the system is given by this expression, where we can find that it's a product of each one of the, I mean, like it's a product of several moments, okay, several qubit values. So it's a simple expression, but when we go for the W state, we can find that the expression is a bit complicated, but we can see that the terms, I mean, like in the GHZ state, we have a exponential fall here, but here we can see that there is it doesn't fall exponentially. To have a better look, we can actually do this
Instead of considering all the particles to be moving with different accelerations, for simplification, we consider all of them to be moving with the same acceleration. Then the expression for the GLG state will reduce as this. C of rho is Ck of rho for k is equal to 1 to n. That's the coherence of each one qubit degrading to the power n kind of thing. And for the W state, we have an expression where we have the highest contribution comes from this 2 here. Okay, so we can see that the W state, the fall of coherence is not exponential. So to check, to look at it in a plot, we consider n-partite GLG state. For the n-partite GLG state, the L1 norm coherence is always equal to 1. And for the n-partite W state, it is n minus 1. So a direct comparison of these two numbers might not give us the right result. So instead, what we do is we define the following quantity. Okay, this CL1 here, what I mentioned here is the non-relativistic value of the L1 norm coherence. Okay, so to compare the loss of coherences due to the relativistic motion, we compute the coherence due to the relativistic motion and divide it by the coherence due to the non-relativistic motion. Okay. And we can see that for the W state, when one qubit is accelerated, there is not much change. Whereas for a GLG state, there is a very high change here. Okay, I'm looking at the 11 qubit system in my plot here. And when I accelerate 10 qubits in the system, for the GLG state, we can see that it falls very fast and there is a lot of coherence is lost. But for the W state, the coherence loss is very low. Okay, so we can do a different kind of a calculation where we find how the coherence is lost when we have two qubit system where one is accelerated, 3 qubit system where 2 is accelerated, and so on. And we find that the coherence falls sort of like polynomially for W and falls a little bit exponentially for GLG state. So the W, from this we can conclude that the W state is actually more robust to relativistic motion than the GLG state. Okay. So what happens to coherence degradation at infinite acceleration? Even at infinite acceleration, what we found was the coherence does not vanish. But this is in contrast to the results due to entanglement, which vanishes in the finite acceleration limit. I'm sorry. Yeah. Okay. Entanglement, which vanishes in the infinite acceleration limit. So this work here, Alice falls into a black hole. In this work, the authors considered a bipartite system in which Alice has one qubit and Bob has another qubit. And Alice, who holds one of the qubits, falls into a black hole, and Bob is at the event horizon of the black hole and is trying to get away from the black hole. And as Alice falls, Bob loses all the entanglement he has shared with Alice. So this was observed in the case of entanglement. But when you look at quantum coherence, such a phenomenon doesn't happen. So we also looked at the local and global coherence for some different states like W bar states and star states. And though from the results, we found that they behave similar to total coherence, and there's not much of interesting results. And from this, we just concluded that W state is more robust to relativistic dynamics than the multipartite GLC state. So with this, okay, I would like to conclude the talk, summarizing what I presented in this. I think we are close to the time. So I think I'll skip over the quantum discord part. So in the work, what we looked at was defining a measure for multipartite coherence with emphasis on separating out coherence which arises due to local superposition and coherence which arises due to correlations between the qubits. Then we used this multipartite coherence to see if it can be used as an identifier or something like something to identify phase transitions in spin chains, particularly infinite spin chains. And then we looked at the effects of acceleration on quantum coherence in multipartite systems. And we found that the multipartite systems, when they are subjected to relativistic dynamics, they lose coherence depending on how the coherence is distributed between the particles. And in a GSZ type of state, when the coherence is distributed in more like a global or a, what do you say, like a more multipartite sense, the coherence is lost much faster than in a W state where the coherence is distributed in bipartite pairs. And for a W state, hence for the W state, the coherence is lost. Coherence is not lost that much. Okay. Okay. Finally, I'd like to thank you for inviting me for this talk. And if I have any questions, I'll be happy to take them now.
Yeah, thank you very much, Radhakrishnan. So you are now open for questions. Is there any questions, students? Yeah, Devanshu, go ahead. Unmute yourself. Devanshu Shekhar.
Hello, can you hear me?
Yeah.
Yes, yes.
Yeah, so thank you for your talk. What I wanted to ask is when you introduced this, what do you call this coherence, you introduced two types of coherence. Like, can you go back to that slide? Actually,
Yeah.
I am forgetting the terms actually.
No worries. I'm going back. We can get this.
Local coherence and something else.
Yeah.
Yeah, intrinsic coherence. So yeah, exactly, that's it. Little bit ahead. The next slide. The expression for the intrinsic coherence.
Oh yeah.
Yeah, so in this case, you are minimizing the distance over all separable states. But in your talk, you also mentioned that you have used the separable states and product states interchangeably. But it's not really this, but they are not really the same. The separable states are a little bit a bigger state, a bigger set of than the product state. So is there any justification to using product state by measuring the distance only from the product state?
Oh, okay. There's a chronological thing in this. Like when I first wrote this paper, I used the separable state and I published it with the separable state. But later on, I actually changed this definition in my subsequent works, like to call this as global coherence and find the difference to distance rather to a product state rather than a separable state. The reason is, if I call something as a separable state, I can still have some kind of correlation or discord.
Okay, you like discord. Yeah, okay.
Discord in them. Okay. I just wanted to get rid of every single correlation, and that's why I changed the definition.
All right. All right. And I was just a bit curious that this minimization procedure over all separable states, how simple is it to do?
It's very hard.
So how do you accomplish in your calculations?
It requires a convex optimization. If you look into the paper by Vedral and Plinio, they have given a procedure where they will tell you like when you have a, let's start with just a qubit system. Okay. When you want to write a separable state for a qubit, you can write it as some product times some tensor of rho A times rho B. Okay.
Right.
Okay. So the number of terms needed to describe, I mean, there is a probabilistically mixing these different tensors, right? So the number of probabilities you need is actually limited by a mathematical theorem called Carothier's theorem, which is based on the dimensions of the system. And that will give you something like 16 parameters or something. And for each density matrix, you will have some parameters. So in total, you will have 80 different parameters. Out of the 80 different parameters, you have one constraint. That is the probabilities of mixing should be 1. So this, you have to optimize over these 80 different things to actually calculate this.
Oh, okay.
It's a very, I mean, like when you write a code for this on a computer and try to run that, I mean, for a 2-qubit system, it doesn't take much time. It does it fairly quickly. The trouble starts when you move to 4-qubit system.
Right. Okay. I will look at that paper. Yeah. Also, sir, for this, when you define this local coherence and you define this rho D, so I understand this is a diagonal density matrix, right?
Diagonal of the separable or the product state density matrix.
Oh, okay. So diagonal of the separable. Okay. That's why I was wondering why it is lying in the separable set.
Yeah.
Okay. Thank you.
So there was a question in the chat box. Lakshmi Prasad Nayak, I could not understand the rho and sigma explanation. Could you explain it again? I hope it was this one. Was it this one? Hello?
I don't know, because the chat box question, maybe who asked it, he or she is not here.
Oh, not here. Okay.
You may answer it, no problem.
Okay, so here actually the density matrix rho is the matrix in which we are trying to measure the quantum property, and the density and the other density matrix sigma is a matrix in which this quantum property is not present. For example, if I consider my density matrix rho to be an entangled state, then sigma is a separable state. That's what I am trying to mean here. That is, you can see that I have put this sigma at something like 0 of a scale. This is 0 of entanglement. And this rho here has some amount of entanglement. So I'm putting it at some point on the scale.
Okay. Any questions? I think no. Okay. If there's no more questions, let's just thank the speaker once again. Thank you, Dr. Radhakrishnan.
Thank you. Thank you.
Organizers? Anyone from the organizers? Okay, so then I'm going off. So you guys